I'm here to talk about power. This lecture will cover power and energy, dynamic power, and static power. For the definition of terms, the instantaneous power, which is consumed or supplied by a circuit element, is the product of the current through the element and the voltage across the element. The energy consumed or supplied over some time interval T is the integral of the instantaneous power. The average power over this interval is, and power is expressed in units of watts. Energy in circuits is usually expressed in joules, where 1 watt is equal to 1 joule per second. Energy in batteries is often given in watt hour, where 1 watt hour is equals to 1 joule per second times 3,600 seconds per hour times 1 hour, which is equals to 3,600 joules. These are the formulas used to compute power in circuit elements with their corresponding biases in relation to different components. Charging a capacitor. When the gate output rises, energy stored in capacitor is computed using the given formula, but energy drawn from the supply is energy from VDD is dissipated in the PMOS transistor as heat. Other half stored in capacitor. When the gate output falls, energy in capacitor is dumped to ground and is dissipated as heat in the NMOS transistor. Switching power can be determined using the following formulas.
Ayan.
Short circuit current. When transistors switch, both NMOS and PMOS networks may be momentarily on at once. Leads to a blip of short circuit current. More than 10% of dynamic power if rise or fall times are comparable for input and output. We will generally ignore this. Power dissipation sources. Total power can be computed with the sum of the dynamic power and the static power. Dynamic power is computed with the switching power plus the short circuit power, while the static power is computed using the summation of the sub-threshold leakage current, the gate leakage current, the junction leakage current, then the contention current multiplied to VDD. Switching power is computed using the given formula. When we reduce dynamic power, we try to minimize activity factor, its capacitance, supply voltage, and frequency. Clock gating. The best way to reduce the activity is to turn off the clock to register in unused blocks. In clock gating, it saves clock activity wherein alpha is equals to 1. It eliminates all switching activity in the block and requires determining if block will be used. Capacitance. A good gate capacitance requires few stages of logic and has small gate sizes, while a good wire capacitance has good floor planning to keep communicating blocks close to each other and needs drive long wires with inverters or buffers rather than complex gate. Voltage and frequency. Run each block at the lowest possible voltage and frequency that meets performance requirements. In voltage domain, it provides separate supplies to different blocks. Level converters required when crossing from low to high VDD domains. In dynamic voltage scaling, you adjust VDD and F and frequency according to workload. Static power is consumed when chip is quiescent. Leakage draws power from normally off devices. Ratioed circuits burn power in fight between on transistors.
Go.
That's the end of the lecture. Thank you for listening.